Right, this is our last lecture for the semester. We have a final exam that's scheduled for 2 Fridays from now. That's on the 16th. And it's pretty early in the morning. It's like 7:30 or something. There is I guess there are a few sample tests from the past that are on the website. The syllabus is posted on the website. So again, as you've been doing for the other 2 tests, do all the preparation you think you need and then try out the sample tests. It'll be a good indicator of whether you're ready to take the last exam or not. Again, as was the case with the other tests, there are no surprises. If you study and if you can do the sample tests, there's no reason why you shouldn't do the 3rd test completely. Okay. All right, you have any questions before I start talking about our last data structure, the R tree? Okay. All right, so today we're going to look at R trees. R trees are, let's see, are you able to read the stuff? We need more contrast. Yeah? It's okay? All right. All right, so, so the R tree data structure is really an extension of a structure we saw perhaps toward the middle of this course. That was the B plus tree. If you recall, in a B plus tree, which itself is a variant of a B tree, we basically had 2 kinds of nodes. We had data nodes, and then we had index nodes. So data nodes formed the leaves of the B plus tree. Index nodes were used to navigate from the root to the proper leaf, where you would find the data you're looking for. All the leaf nodes are at the same level, and then there were constraints on the minimum and maximum degree for an index node. Okay. All right, so an R tree is really an extension of the ideas used in the B plus tree. Okay. It's used to store multidimensional objects. Okay, so you might, in 2 dimensions, you might be storing a collection of, say, rectangles, where you interpret rectangle in its most general terms. So a straight line is a rectangle with very small width or very small height, and a point is also a rectangle. Okay. So in 2 dimensions, for example, we may want to be storing this collection of objects. Okay. So the greens are the rectangles, and I got some blue points. I don't have any lines in this example. And then you want to be able to insert rectangles in time. You want to be able to delete rectangles in time. You also want to be able to perform queries. Typically, the kind of queries you perform here are intersection type queries. So you may be given a query rectangle and find all the objects that intersect that query rectangle. Okay. Now you can use it to represent non-rectangles, objects that are not really rectangular also, by enclosing these objects in minimum bounding rectangles. Okay. So if I wanted to represent these 4 objects in my, say, 2-dimensional R tree, what I would do is I would bound this with what we'll call an MBR, minimum bounding rectangle, and I'll use this as kind of a surrogate for that. Okay. And eventually, when you do your search and you want to find an intersection, your search will get you here thinking you have a rectangle, and then to verify that you actually have an intersect, you'll have to go back and do an intersect with the actual object. Okay. So similarly, that cross would be represented as a rectangle. A U-turn is a rectangle in that odd shape as a rectangle. Okay. All right. So as I said, it's an extension of a B plus tree. So you have 2 types of nodes. You have data nodes. These are the leaves of the R tree. And data nodes will contain the objects that you're storing. Just like in a B plus tree, the data nodes stored the objects in your dictionary. Here, our objects happen to be rectangles. Then you have index nodes. These are the interior nodes. These are used to navigate yourself to a proper leaf. So if you think of the structures, if you're sitting at a node in the structure, then that node is going to, if it's a leaf, it's going to comprise some number of rectangles, your data objects. If it's an index node, it's going to contain the minimum bounding rectangles for the objects stored in the subtrees. Okay. So if a node has 4 subtrees, it'll contain 4 minimum bounding rectangles, one for each of its 4 subtrees. We'll see an example to make that a little bit clearer. Okay. All right, so first the definition before we look at an example. So you have an order M associated with an R tree. Okay. So the requirement is that every node other than the root, okay, must have a certain number of rectangles stored in it. Again, I'm using rectangles in a general term. A rectangle could be a data object, like in a leaf, or it could be a minimum bounding rectangle as stored in an index node. Okay. So the number of rectangles in a node other than the root has to lie between some minimum number and some maximum number. Okay. The maximum is M, that's the capacity of the node. Then there's a lower bound requirement, which if this was a B plus tree, it would be something like this. Okay. But you get a little bit flexible, and you, in practice, permit people to use lower bounds that may be smaller than M over 2. Okay. Now in our discussions, we'll just assume that the bound is ceiling of M over 2. So each non-root has to contain at least ceiling of M over 2 rectangles in it, and at most M rectangles. Okay. And again, in practice, typically people use that, but not always. They do sometimes go below that. Okay. Okay. You have a relaxed constraint for the root. The root can contain anywhere from 1 to its capacity M rectangles. Okay. The number of rectangles in an index node equals the number of children it has. This is another place where this definition differs from that of a B plus tree. Okay. 2 places where we differ. One is here. In a B plus tree, you have a definite lower bound of M over 2, whereas here, at least in practice, people tend to use things that may be smaller than that. The other one is out here. If you think back to a B plus tree, the number of data sitting in an index node is 1 less than the number of children. Okay. So if you've got 4 nodes, then you may store the largest value, say in this, or the smallest value in the second subtree, smallest in the third, smallest in the fourth. Okay. So in a B plus tree, the number of data in an index node is 1 less than the number of children, but here the number of rectangles in an index node exactly equals the number of children that the index node has. And then the standard B tree type requirement, all the data nodes or all the leaves are at the same level. Okay. All right, so the definition is very similar to that for a B plus tree. There are some minor changes or differences. Let's look at an example to try and crystallize these ideas or concepts. We'll construct an R tree of order 4 for a collection of rectangles in 2-dimensional space. Okay. So in such an R tree, okay, the capacity of a node is 4. So a data node can have up to 4 rectangles in it. An index node can have up to 4 minimum bounding rectangles in it. If you are the root, you can have as few as one minimum bounding rectangle. If you're not a root, you got to have at least two. Okay, m over, so half of your order. Okay. All right, so here's my collection of two-dimensional rectangles. The first question that may arise is, well, how do you decide which of these rectangles gets grouped into a leaf? Okay. There's really no ordering relationship on a bunch of rectangles. You could, for example, take these 4 rectangles and put them all into one group and put them into a leaf. Okay. Or you could take this rectangle, this point, and that rectangle and put them all into a leaf. Okay. So the structure really doesn't place any constraint on how you select the rectangles that go into a data node. It's legitimate to take any subset of your rectangles so long as you don't take more than m. And of course you got to have at least m over 2 unless you happen to be the root. Okay. All right, so let's look at a possible grouping of our rectangles into leaves, and I'm going to group them into a total of 12 leaves, because this is possible only if you have at most 48 rectangles. Okay. All right, so my first grouping will contain these 4 rectangles. I'm going to toss them all into one leaf node or one data node. Okay. And in red, I've got its minimum bounding rectangle. Okay. So the parent of this data node will contain this red rectangle in it. Okay. Even though this rectangle here overlaps with this minimum bounding rectangle, this rectangle or a part of it is not stored in this node. Okay. So in an R tree, you don't take a data object and chop it up into pieces like we've been doing with some of our other structures. The entire object is stored in a single place. Okay. All right, so here's another grouping that I'm going to have, and again in red I've got its minimum bounding rectangle, and this leaf or data node will have these 4 rectangles in it. There's another one for my third leaf. Here's one for a fourth leaf. Okay. So I'll have these 4, because it's not necessary to have 4. Okay. Anything between 2 and 4 will do. And as you can see here, minimum bounding rectangles may overlap. Okay. All right. So you got another one there, 3 rectangles and a point, and again we have an overlap between minimum bounding rectangles. Okay. Right, here's my 7th rectangle, another one. Okay. All right, so I've taken my collection of two-dimensional rectangles and partitioned them out into 12 groups. No group has more than 4 rectangles in it. Some of them don't have 4. For example, this one here only has 3. Okay. But the only requirement is that you got to have at least 2. Okay. All right, so this is a possible grouping of my data objects into data nodes. Okay. All right, a possible R tree. Okay, we just look at the structure. Okay, so I'm going to have 12 leaf nodes. The leaf nodes are the data nodes. Okay, and these are going to all have to be at the same level. Okay, so the data nodes have parents which are index nodes. The number of rectangles in each of these will be a minimum bounding rectangle. Number of rectangles stored in an index node exactly equals the number of children that the node has. So this node has got 4 children, there's the leaves, you have 4 bounding rectangles. This one here has got only 2 children, so it's got 2 rectangles in it. This guy's got 3 children, it's got 3 rectangles. This guy's got 3 children, so 3 rectangles. Okay. All right, so these things here label rectangles, which we'll identify in a moment. Okay. But this A is the minimum bounding rectangle for the 4 rectangles stored in this node. Okay. The B here is the minimum bounding rectangle for whatever data is stored here. C is the minimum bounding rectangle for whatever is stored here. Okay. All right, so these index nodes will also have a parent. Okay. And the number of rectangles stored in this node will be exactly equal to the number of children that it has, which happens to be 4. Okay. The M out here is the minimum bounding rectangle for A, B, C, and D. Okay, so you got 4 rectangles here, so they have an MBR which includes all of these 4 rectangles. That's going to be M. The N out here is the minimum bounding rectangle for E and F. O is the minimum bounding rectangle for G, H, and I. P is the minimum bounding rectangle for J, K, and L. Okay. All right, so let's see that at work with our example. Okay. All right, so these bounding rectangles here give us the groupings we had decided on a little while ago. So let's suppose that okay, so this leaf out here represents this rectangle. Okay, so it's got these 4 green rectangles in it. The next leaf, B, represents this grouping, so it's got these 3 rectangles in that point. And then its sibling represents this rectangle, okay, and its sibling represents this one. Okay. Again, at this point is just a matter of choice. I've decided to take these 4 groups and make them all siblings out here. Okay. There really aren't any rules at this point to say how you select which groups become siblings. You can do it any way you like, and you'll still be able to build a tree. All you will affect is the search complexity. Okay. The number of nodes that get examined when you do a search will differ depending upon how you group the original data and then how you group minimum bounding rectangles at higher levels. Okay. All right, so let's suppose that I've chosen to make A, B, C, and D, okay, these 4 groups siblings. Okay. Then this A represents that bounding rectangle, and then the B out there is this bounding rectangle, and so on. Okay. Now, the M out there, okay, right, that's this fellow up here. This M is going to be the bounding rectangle for A, B, C, and D. Okay. So it's going to be this big red rectangle that I just gave you. Okay. So you take the minimum bounding rectangle for A, B, C, and D, that becomes M. Okay. All right, suppose that this is our E and that's our F. Again, you could just as well have said that's your E and that's your F. Okay. But let's suppose that's our E and F. Okay. Then here, these 4 rectangles are stored here, and these 4 are stored over there. Okay. And then E represents this bounding rectangle, and that F is this bounding rectangle. The parent N out there is going to be the bounding rectangle for E and F. Okay. So the parent will be that rectangle. All right, if I look at the sibling of this node, that's got a G, H, and I. Okay. Any of the remaining subgroups are candidates for G, H, and I. And I'm going to assume we chose it this way. Okay. Then in the root, we have a bounding rectangle O. which is the bounding rectangle for G, H, and I. So it's going to be that fellow. Okay. All right, then for the last guy, you don't have any choice. So we've got JKL would be these three fellows, and then the bounding rectangle for JKL is P, which is sitting in the root. All right, so an R plus tree is basically a B plus tree, which stores multidimensional objects. We've seen other structures that could be used for multidimensional objects, but those are mostly binary tree type structures. Here we have a high degree tree, which makes it suitable for storage on a disk. So you can reduce the number of disk accesses made. So if you really have a very large collection and you want to store them on a disk, you wouldn't want to use a binary tree type structure. Okay. All right, any questions about what an R plus tree is before we look at how you perform queries, inserts, and deletes? Yeah.
Is there any ordering of M and O?
Is there any ordering of M and OP up there? Well, the only ordering that comes is once you have decided this is the leftmost child, then M has to occupy the first position. But this could easily have been here, and that could easily have been there, in which case this would look like NMOP. Okay? So there are really no constraints on how you order the siblings or anything. Okay. All right, any other questions? Okay. All right, so the kind of queries that you support are intersection queries. So somebody gives you a query rectangle, and you need to report all of the objects in your collection that have some overlap with this object, or with this query rectangle. Okay. All right, so in blue, I've got a query rectangle. I want to find everything in my collection that overlaps with this. So I want to report this object, that object, that object, that object, and that one. All right, the way you do it is you start at the root of your R plus tree, and you look at the MBRs that are stored in the R plus tree and see which ones have an overlap with the query rectangle. Those are the subtrees you have to search. And you recursively apply this rule at all levels till you get down to a data node, and there you do a real intersection with the data that's sitting there. Okay. All right, so the root of our R plus tree has 4 MBRs, and M, N, O, and P. So that's what you see at the root. That's your query. So you see if the query intersects M, it does. It intersects O, and it intersects N, but not P. So there are 3 subtrees that you have to search. Okay. So I'll search those 3 subtrees recursively to report the fellows that intersect. Okay. So when you're searching M, okay, we go down to that leftmost child of the root, and over there we find these 4 bounding rectangles. Okay. So you run your intersection test against these 4 bounding rectangles, and you find you have an overlap with that rectangle, you have an overlap with this one, not with that, and not with that one. Okay. So now you find your way down to 2 data nodes in that subtree. Okay. And then each of those has 4 rectangles, or at most 4 rectangles, and now when you get here, you got to see if any of those 4 intersects with this. And then when you get in here, see if any of those 4 intersects with that. If so, you report them. Okay. All right, so that's how a search works. All right, if you want to perform an insert, again, at some level, the ideas are pretty much the same as those employed in a B+ tree. But since there is really no rule to tell you how you group rectangles together, the new object you're inserting could, at least in principle, go into any one of your data nodes. Okay, there's nothing to stop you from putting it into any one of the data nodes in there. You have total freedom to do that. And if the data node you're trying to put it into exceeds its capacity, you'd have to split it. Okay, so you can put it any way you want, and if the capacity is exceeded, you need to split. And so we have some flexibility here in trying to build an R tree which can be searched efficiently. Okay. If you think back at the search algorithm we looked at, its complexity in terms of number of nodes you actually visit depends a lot on how you did the grouping. Okay. So you'd like to build it so that the probability of searching too many nodes is reduced. Okay. And this is where you have leeway. Okay. So you need some rules to tell you which leaf should you insert the new data object into. And then when a split takes place, you need some rules to tell you how do you do the split. Okay. Now, there really aren't any rules around that you can say, well, theoretically, this is the best way to do it. Okay. So you end up using heuristics which have good intuitive appeal. Okay. So first, let's take a look at leaf selection. Okay. To determine the leaf, you really have to start at the top. Okay. I mean, you can't examine all of your data at this time to decide which leaf to go into. You really have to start at the top, and at each index node, you have to make a heuristic choice which subtree to move into, and finally, whichever leaf you reach, that's where you'll make the insert. Okay. So you're going to follow a path, and to guide you in the path to follow, it's a heuristic really, you take a look at your choices, okay, and say, well, if you moved into one of these subtrees and you made the insert there, well, that would change the MBR for the collection of data stored there, and by how much would you change the MBR, the minimum bounding rectangle? Okay. So the heuristic here says, of your choices, move into the subtree whose minimum bounding rectangle area would increase the least. Okay. The rationale for this is when you do a query, okay, the probability of moving into a subtree is related to the area of that MBR. So if you got a large area, you have a higher probability a query will cause you to move into it. If you have a small area, you have a smaller probability of moving into it. Okay. So based on that simple intuition, you end up with this heuristic which says try to keep the MBRs of your rectangles, of your covering rectangle, try to keep the area of the MBRs as small as possible. Okay. All right, so I'm trying to insert a rectangle into my example R tree, and this is what I see at the root. Okay. And here is the rectangle I'm trying to insert. Okay. Well, if I insert it into the leftmost subtree, okay, then the MBR is going to change from M to this one. Okay. So the area of my MBR goes up by this amount. Okay. If I put it into the next subtree, the MBR of that is N, and if this rectangle goes there, the MBR is going to look like this when you're done. And so the area changes by the area of this big rectangle minus the area of the original one. Okay. So that's the increase in area. Okay. If you put it into O, okay, your new MBR would look like that. So it's this much area by which you go up. And if you put it into P, okay, you go up by that. Okay. So you do this computation on all of your choices and figure out which choice yields the smallest area increase, and that's where you do the insert. Okay. All right. So that tells you how to go down to do an insert. Eventually you reach a leaf node. If the leaf isn't already full, you can place your new object in there. If the leaf is full, you have to split it. So now you have to decide how do you split. You have total flexibility. The only requirement is that the two new leaves must each contain some minimum number of rectangles, that's little m, in our example 2, and no one should contain more than 4 in our example of big M in general. Other than that, you can split any way you like. Okay. Right, so we've got m plus 1 rectangles. We need to split them into two sets A and B. Okay. Each of them has to have the minimum number. And of course, no one can have more than m. Okay. And the heuristic that's used to split here is you want to do it so that the sum of the areas of the rectangles A and B that you create is minimum. Okay. So the subsets A and B have MBRs. You measure the areas you want to pick. Okay. Again, the rationale is the same. If you keep the areas small, then the probability of having to search them becomes small. Okay. Okay. All right, so let's reach a leaf, and this is an example with big M equals 8 and little m equals 4. So I reach a leaf, it already has 8 rectangles in it. I'm going to insert this red one, it now has 9. I need to split it. So one possibility is to have A, which has these 4 in it, okay, and then the other 5 go into B. So you compute the area of this blue rectangle and the area of that yellow one. Another partitioning is like this. So the blue one has these 4, sorry, those 5, and then the yellow one gets the 4 down there. Okay. So depending upon how you partition, you get different areas. Okay. All right, so the question is, well, how do you pick? Simplest strategy is to just try out all possible choices for A and B. Okay. And for each choice, you just compute the area of the MBR of A and the area of the MBR of B, add them up, find the min across all possible choices. Okay. Once you pick A, B is fixed. Okay. Right. So if you're looking only at A's that have exactly M, the minimum number in them, okay, then you've got to wrestle with that many choices, the number of ways you can choose M items out of M plus 1. Okay. Now, if you're dealing with small degrees, that's not too bad, but if you're dealing with large degrees, that's a expensive computation. Okay. So people then really resort to what you might call heuristics, clustering type strategies. Okay. So use a clustering strategy, and if you're familiar with these, typically the way you build clusters is you seed them. So you start with a candidate object in A and a candidate object in B, and then you grow these clusters, say one object at a time. Okay. So you grow A and B, and the growth in this case continues, okay, until you have assigned all of your rectangles. Okay. All right, so you need a seeding strategy. then you need a growth strategy. Two popular strategies to cluster for our trees. One is called the quadratic method. The other one we're going to look at is the linear method. Okay. Right, the quadratic method, as the name suggests, is going to run in square of m time. All right, so we've got m plus 1 rectangles that need to be partitioned into two groups or two clusters. So first I'm going to find a seed. Okay, so this is the seed for cluster A, that's the seed for cluster B. Okay. And the way I select the seed is by maximizing this function. Okay. What does this function give you? Right, so here I've got the minimum bounding rectangle of the two seeds. Okay, now look at the area of that. And from that I subtract the area of each of the seeds. Okay, so in some sense this measures the penalty associated with putting A and B into the same cluster. Okay. This is the amount by which the area of this cluster grows. Individually they only had this much area, but together you end up with this much. So this gives you the amount of unused space in that MBR. So it's a penalty function. Okay. So you find two rectangles for which this penalty function is maximum, and then you start by putting them into different clusters. Okay. All right, so let's say this is my collection of rectangles. I want to find two seeds. Okay. If these are my A and B, then the MBR is this. So the penalty associated with putting these two fellows in the same cluster at this time is the white space in that rectangle. Okay. So the white space is MBR of the area of the MBR minus the area of the two blue boxes. Okay. That's what that penalty function has. Okay. If you put those two fellows in the same cluster, then the MBR is given by the red rectangle, and the penalty is the white space, so that's the area of the red rectangle minus the area of the two blue ones. Okay. So you have more to lose by putting these two fellows in the same cluster than we had by putting the previous two. Okay. So we find two rectangles that have the highest penalty if they were put into the same cluster, and we use those as seeds for A and B. All right, so for this you got to try out all m square possibilities and pick the one with the maximum penalty. Okay. Right, so once you've got the seed, then you look at your rectangles and grow these clusters. These clusters have one rectangle each now. We're going to now grow them one at a time. And to grow, you select a rectangle that's not yet assigned to a cluster. Okay, so examine all the rectangles not yet assigned to a cluster, and I compute this function. Okay. This says if you take a rectangle C and you put it into cluster A, okay, then the penalty, by how much does the area of cluster A go up? This is the new area of cluster A, that's the old area of cluster A. Okay. So if I put C into cluster A, its area would go up by this much. But if I put C into cluster B, its area would go up by that much. Okay. So this difference tells me how much of an affinity does C have for A over B. If this difference is 0, as far as C is concerned, it doesn't matter where you put it. If this difference is huge, either positive or negative, then C has a big affinity either to go here or to go there, okay, versus the other cluster. So we're going to pick a rectangle that has a relative high affinity for one of the clusters and then put it into that cluster. Okay. All right, so let's say I've seeded, this is my cluster A, that's my cluster B, the yellow one. Okay. I look at this rectangle. Okay. If I put it into cluster A, the penalty is the white space. Okay, look at this bounding rectangle area minus this blue area minus that. sorry, I'm looking at, okay, this is my new MBR, okay, and then I look at the old MBR as this one, okay. So I subtract the area of the new MBR and the old one, so the penalty is, I guess really this whole thing here, less that. Okay. So that's the cost of growing this cluster by adding this rectangle. Okay. If you took this rectangle and put it in there, then your cost is the area of this big rectangle minus the yellow one. Okay. So you look at the difference between these two costs, and you see that this one has a preference for being here versus being out there. Okay. And the difference in the cost tells you how much of a preference does it have for being here versus there. Okay. All right, then you try it out with another rectangle. Okay. And this guy's cost is this big area minus this blue one. If this guy went over there, it would be this huge rectangle minus the yellow one. Okay. So this guy also has a preference for being here over there, but the relative preference is much more for this guy than it was for that guy. Okay. So we would prefer at this round to put this guy in here than to put that guy in here at this time. Okay. So you try this out over all of them and figure out which one has the highest relative preference to be in one of the clusters, and you put it in. Okay. All right, so once you found the C that maximizes the objective function, you put it into the appropriate place. Okay. All right, and then you continue this. In each round, one rectangle gets assigned. Okay, that's how you do the split. Okay. All right. There's a linear method. Over here, you look at normalized separation. Okay. So if you take two rectangles, you measure their separation in the x direction, which is defined as the, okay, you take the largest left edge and the smallest right edge of the two rectangles, okay, and subtract the distance. Okay. So if you're looking at the normalized separation, this blue and that yellow, you look at the largest left edge, that's this one, and the smaller right edge, and subtract the distance. So you find the rectangles which have the maximum x separation, and you divide that by the spread in x values to normalize. Okay. You do the same thing in the y direction. You look at the largest bottom and subtract from that the smaller top. Okay. Largest bottom minus smaller top. In this case, you get a negative number. Okay. And here again, you would take the larger bottom minus the smaller top. So you get a positive separation. Okay. And then you normalize by the y spread. Okay. The pair of rectangles that have the maximum normalized separation are used as the seeds. Okay. All right, so once you've got the seeds, okay, then you take the other rectangles in some random order, and you assign them to whichever rectangle they have a preference, whichever partition. Okay. And so that's just done by looking at how much the MBR goes up if you put it into A versus into B. Okay. And so this process runs in linear time. Okay. So those are the two more popular ways of doing the split. Okay. Right, finally we have the delete operation. So to do a delete, you have to find the rectangle. So we use the query algorithm to find the rectangle. Then you reach a leaf. You take the rectangle out. If the capacity hasn't gone below the minimum, you're okay. If it's gone below the minimum, you need to do what you would do when you're dealing with a B plus tree. You try to borrow from a neighbor, and when you borrow, you have to readjust the MBRs. Okay. And if you can't borrow, you do a combine. Okay. And then you have to redo the MBRs. Okay. So as far as delete goes, there aren't any new ideas really here. Though it's probably worth mentioning that some people, instead of just doing the B plus tree type of delete, they use the delete as an opportunity to reorganize the whole structure, or at least do a more than just this, but try and do some optimization on the partitionings. Okay. But that could get pretty expensive. Okay. All right, so basically that's what an R tree is. It's an extension of a B plus tree used to store objects in multidimensional space. You can perform queries, searches, and inserts. Performance depends a lot on how well these heuristics function in terms of getting you partitionings which don't require you to search too many nodes. The structure is used quite a bit in robotic type applications. You've got all kinds of objects sitting in, say, three-dimensional space, and people are moving around. You need to be able to tell who would you hit if you moved in a certain direction, say. Okay. There are a number of variants of this structure. I have time maybe only just to mention the names. I'm going to kind of skip the little descriptions that might come with them, so you're at least familiar with the names. There's something called an R plus tree, very similar to an R star tree. There's a Hilbert R tree. They're quite similar to the R tree that we've looked at. There's an R plus tree. What this one does is it doesn't allow overlapping MBRs. So if you don't allow overlapping MBRs, you have to accept cutting objects into pieces. So some object may fall into 2 or more MBRs. Okay. So you cut objects into pieces, and they have to relax the upper and lower bounds on data stored in a node in order to make the inserts and deletes somewhat manageable. Okay. So this structure can end up in a degenerate case where you only have a long chain of nodes because there's really no enforcement of lower bound of a node. Okay. But again, in practice, you tend to get good balance even though you're not enforcing the lower bound. Okay. All right, finally, there's something called a cell tree, which combines ideas from the binary space partitioning tree we looked at last time and the R plus tree that I very briefly mentioned a second ago. Instead of using MBRs, you use convex polyhedra to divide the space out. That reduces the amount of white space in a region, white space being the space that's not occupied by objects in your data set. And so hopefully that reduces the number of nodes you have to visit. Okay. All right, again, as far as leaves go, they don't enforce any lower and upper bounds. When you're not going to allow overlap of MBRs, you really can't have an upper bound on the capacity of a leaf node because you may have a large number of rectangles that overlap and cover the same point. But they do enforce a lower bound on the degree of an index node, and so you can't get a degenerate version here. Okay. All right, so that's about all I had to say on R trees. You have any questions? No? Okay, well, hopefully you can have a good final exam. Normally I would call it a final, a good third exam. Okay. All right.